All right. So the next concept that we are going to move to is this idea of solubility. So far we've kind of been just accepting that whatever we're putting into our aqueous solution is going to dissolve, and if it's an ionic compound, it's then going to further dissociate into the ions. That may not always be the case. So there's something called solubility. Solubility is the maximum amount of that solute that you can dissolve in a very specific amount of solvent. And of course it is dependent on the temperature. So if you've ever made Kool-Aid or tea, you know the sugar dissolves much more readily in the hot water than the cold waters. And this is often expressed in terms of grams of solute per 100 grams of solvent. And again, the solvent is usually water. We have grams per 100 grams of water. What do you think this is going to act like? Conversion factor. It's a conversion factor. We got fractional units again. And again, the solubility is that maximum amount. Once we've added that maximum amount, what's going to happen? You're close. I think you're getting to the concept. You're going to have solid just hanging out. It can't go any further into solution. If you're like me and you like a little bit of tea with your sugar, you usually have extra solid sugar sitting at the bottom of the cup. That's because you've reached the solubility limit. You've added as much sugar, and as much sugar that is able to dissolve has dissolved, and all of the rest of it's just going to stay solid. It can't dissolve anymore. And so depending on whether or not you've reached that solubility limit, if you have a saturated solution, so you've put in as much as you can, as much as possible has dissolved. If you haven't reached that limit, you have an unsaturated solution, and you can add more to it, and it will continue to dissolve. Notice that you have two arrows going in this direction. In a saturated solution, you're not really sitting there stagnant like nothing's happening. You have an equilibrium happening. So for each molecule that is able to dissolve, one of the molecules that was in solution recrystallizes out as a solid. And so you have this equilibrium turnover happening in your saturated solutions. So I mentioned that way easier to get all of your sugar to dissolve in hot water than it is cold water. How many of you have made rock candy? What? You guys have been deprived. All right, I'm going to figure out a way for us to be able to get some rock candy going. So rock candy is a unique candy structure where you create a supersaturated solution. And so by creating a supersaturated solution, what you do is you increase the temperature of your solvent, the water, so that more of your solute, which in this case is sugar, will dissolve. And then you very carefully reduce the temperature. And if you are very careful about it and you don't have any defects in your pot or anywhere that the solid can start forming, what you'll be able to create is a supersaturated solution. All of the sugar that's in solution will stay there. And then as soon as you introduce a stick to make your candy, as soon as you introduce a place where the solid can start forming or nucleating, it's going to start doing that. And when it does that in the rock candy, that excess sugar that's in there comes out and makes solid crystals on your stick, and you have delicious rock candy. But all of that is based on this idea that temperature will impact your solubility, and temperature impacts the solubility of your solutes differently. Even for your solids, adjusting the temperature will change the solubility of your solids differently. Some solids changing the temperature will drastically increase their solubility, some of them a little bit. But what do you notice about increasing the temperature for every solid? Do any of them get less soluble? No, they all get more soluble. Sodium chloride stays kind of flat, right? But none of them go down. What do you notice about your gases? They all go down. So you have this inverse relationship between the solubility and temperature. As you increase the temperature, you're going to increase the solubility of your solid material. But as you increase the temperature, you're going to decrease the temperature of your gases. So this is why your soda at room temperature will go flatter faster than your cold soda. Because when you increase the temperature of a solution that has a gas in it, the solubility of that gas goes down. This leads to some really interesting questions. And so a really good exam question that comes out of this concept is you'll be asked about a saturated solution. So if you have a saturated solution, that means it's at its solubility limit, and it's saturated for both potassium iodide, so we've got a solid, and carbon monoxide, a gas, at 20 degrees Celsius. What's going to happen if we increase the temperature to 40 degrees Celsius? Are we going to see nothing happen? Nothing's going to change. Are we going to see potassium iodide coming out of solution because we're decreasing the solubility of the potassium iodide by increasing the temperature? Are we going to see bubbles of carbon monoxide forming because we're decreasing the solubility of the gas by increasing the temperature? Or are we going to see both because we're decreasing the solubility of both by increasing the temperature? So we're increasing temperature. Which one of them, so the solid or the gas, is going to have a decrease in solubility? The gas. So what are we going to see? What do you see in your soda? Carbon dioxide. But you see bubbles. When you decrease the solubility of a gas by increasing the temperature, the gas bubbles out. So when you decrease the solubility, that one comes out. And so we're going to see bubbles of carbon monoxide forming. Flip this question around. What would you expect to happen if instead of increasing the temperature, we decrease the temperature? You're going to start to see the solid because you're going to decrease the solubility of that solid potassium iodide, and it's going to start to come out of solution. The other thing that will impact the solubility, especially for gases, is pressure. And so when you crack open your soda, what do you hear? You get this beautiful fizzy sound, which is actually not that great because that means the carbon dioxide is escaping and your soda is getting ready to go flat. And so when you have a high pressure above your solution, it helps to push all of that gas down into solution and keep it there. But when you decrease the pressure pushing down on your solution, the gas can start escaping. And that's known as Henry's law. And Henry's law is this idea that the solubility of gases is directly related to the pressure above that solution of gas and liquid. And the higher the pressure, the more soluble that gas is, the more it's going to be pushed into solution. This is really important from a medical standpoint for people who do a lot of scuba diving. When you go and you go under the ocean, you're increasing the pressure on your body, and your blood has dissolved gases in it. And when you increase the pressure on the solution, when you increase the pressure on your body, you increase the solubility of those dissolved gases, and you get more gas dissolved in your blood. If you surface too quickly, if you decrease the pressure on that gas solution too quickly, so you're going to start having the solubility of those gases decrease, they're going to start to bubble. Bubbling blood does not feel good. That's called the bends. And the treatment for that, as a medical professional, you'll want to know this, is hyperbaric chambers. So hyperbaric chambers are high pressure chambers. What they do is they put you back under pressure and then slowly bring you back up. So they redissolve all of the gases to stop the bubbling, and then they slowly decrease the pressure so that the solubility transition isn't so drastic. From a chemist perspective, what we're more interested in is when do the solids start coming out of solution, especially if we have a chemical reaction. So if we reach the solubility limit, we expect solid to start coming out. If we have a reaction that creates something that is not very soluble, that solid is going to come out. That's called a precipitate, and it's a precipitation reaction. And I showed you an example of one of these, my favorite. It makes that beautiful purple precipitate earlier. And the way that we work with these is we look for things that don't have a high solubility in water. So there are salts that are really low solubility. You're not going to be able to get very much of them to dissolve. And if we put together reactants that make one of those salts that are really low solubility, we can expect that that salt will form a solid. And so there are some rules that we have called the solubility rules that give us an idea of the most common compounds that are going to be soluble. They're going to have high solubility. If it's not on this list, or it's an exception on this list, it's going to be really low solubility, and it's going to tend to form that solid precipitate. And so anything that contains lithium, sodium, potassium, rubidium, cesium, or ammonia is always going to be soluble. It's never going to form a precipitate in solution. So sodium chloride, really soluble. Lithium chloride, really soluble. Ammonium phosphate, really soluble. You're not going to see a solid of that in solution. Our negative ions, anything with, oh, what is that one? NO3 is
nitrate.
8?
Nitrate.
Close. Nitrate or acetate is going to be soluble. So lithium nitrate, calcium nitrate, calcium acetate, those are always going to form aqueous solutions. They're never going to form a solid precipitate. Things with chlorine, bromine, and iodide, they tend to be soluble. So they tend to form just a regular solution. We're not seeing a solid with these. Sodium chloride, potassium bromide, calcium iodide. There are, however, a couple of exceptions to be aware of. If you have one of these three and it happens to be paired with silver, lead 2, not lead 4, lead 2, or mercury 1, it is not soluble. And so if we were to produce silver chloride, we would see a precipitate. We would see a solid forming because silver chloride is not soluble. It is insoluble in an aqueous solution. Sulfate is another one that tends to always be soluble, so it's not going to form a solid. So if you have potassium sulfate, that's going to be a nice solution. But if sulfate happens to be paired with barium, lead-2 again, no, look for lead-2, that's a common culprit. Calcium, strontium, or again, mercury-1, you're going to see a solid precipitate forming. And so if I have a reaction that forms calcium sulfate, I'm going to have a precipitate of calcium sulfate. Calcium sulfate is going to be a solid formed. And that's the most common types of questions. You can either be given a compound and ask, is it soluble or insoluble? Or you can be given a reaction that produces a product and ask, is this going to be a precipitation reaction? Are we going to see a solid form? You're going to go back to these solubility rules. Now, before you go, oh no, solubility, am I going to have to memorize these? No. You remember on your data sheet, this is that nice table that's been sitting there very patiently waiting for you to use it. It's going to be there. It's not there on the final though, but we'll discuss when we get closer to the final some key things that'll help you for that. And so let's start there. Are these soluble or insoluble? All right, cadmium sulfide, soluble or insoluble? We've got to vote for insoluble. What if it was cadmium sulfate? Yep. If this was our product in a chemical reaction, we wouldn't see anything happening. We wouldn't get a solid. It would be considered no reaction. By the way, cadmium sulfide is also soluble. Your book doesn't contain this line here. Usually has sulfur as well, but your book doesn't have it, so it's okay. So cadmium sulfide is going to be soluble. Why? Because the sulfate is generally soluble and it's not paired with any of these exceptions. Good. What about sodium sulfate? Soluble as well, same reasoning. Sulfate is generally soluble and sodium is none of these exceptions. What about lead iodide? And not just any lead, what charge is that? Lead-2 iodide. Oh, lead-2. That should be a red flag anytime you see it. So lead-2 iodide, soluble or insoluble? Insoluble. Why?
When iodine is combined with either gold,
silver,
lead-2 plus, or
mercury-1. Good. Yeah, iodide would normally form a soluble compound, but in this case it's bound with one of these three, and so it's going to be insoluble. Nickel nitrate, soluble or insoluble? Soluble. Why? Because nitrate is always soluble, Dr. Wren. Can't you read? All right, good job.
This might be a dumb question. We probably talked about it, but on that mercury 2, What is that 2 on the bottom?
That's what makes it mercury 1. So a little bit further than we will dive into, this is called a dimer. And so even when mercury forms a compound, it's going to have those 2 atoms of mercury at all times for the mercury 1. Now, if it was mercury 2+, so it was actually mercury 2, you'd only have 1. So mercury is kind of a unique compound in forming a dimer in order to form some compounds. It's a little beyond what we need to know. And we said that based on these things, since we can predict whether these are going to be soluble or insoluble, and we know how to write reactions, especially double replacement reactions, and we can predict the products of those, we should be able to take that compound, look at the compounds that are potential products, look at our solubility rules and decide, are we looking at a precipitate reaction, and in which case we're going to see a solid forming, or are we looking at essentially no reaction where both of our products end up being aqueous. All right, so I'm going to give you an opportunity to try one of those reactions on your own. So this is going to be a double replacement reaction. So everybody's going to swap partners, and you're going to look at the solubility rules to predict whether those products are going to be soluble or insoluble. If they're soluble, you basically have no reaction because it's all just ions hanging out in solution. If it's one of the products is insoluble, you have a precipitation reaction. So I'd like for you to try that with two different reactions. Potassium nitrate reacting with magnesium sulfate. And those are both aqueous solutions. And then silver nitrate reacting with sodium chloride. And remember, when you're doing a double replacement, you're just going to swap the places of the cations. And your products also have to have a cation paired with an anion, and it has to be charge neutral. You've forgotten how to finish out those double replacement reactions and build charge-neutral compounds. All right. I'm gonna move this out of the way for now so we can write our products up. So in a double replacement, we're gonna switch places with our cations. So potassium's gonna switch with magnesium, and we're gonna form magnesium nitrate and potassium sulfate. But now we need to make sure that these compounds are charge neutral compounds. If we want to balance our chemical equation, we have to have the right compounds built. And they're going to form charge neutral. So what's the charge on magnesium? Nitrate. It's 1. When we're building compounds, we do not use coefficients. Coefficients out in front tells us how many molecules we need. Subscripts tell us how many atoms we need. Gesundheit. And so bringing down and across, we need 2 nitrates and 1 magnesium. What's the charge on potassium? +1. Charge on sulfate? -2. So how many potassiums do we need? And that's going to be a subscript, not a coefficient. Now at this point, you can either go ahead and balance it, or you can look and see if you even actually have a reaction occurring. All right, because some of you guys really do need the extra practice for balancing. I'm going to balance it, but on an exam, you'd probably want to see if you have a reaction to see if it's worth your time. So to balance, I have 1 potassium, 2 potassium, 1 nitrate, 2 nitrate, 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. Again, I like to start with the most complicated anion, which is our nitrates. I have 2 on my product side, only 1 on my reactant side, so how do I balance that? Put a 2 in front of my potassium nitrate. What that says is I need 2 molecules, or 2 moles of potassium nitrate for this reaction to occur, which means I now have 2 potassium. Oh, I already took care of my potassium imbalance too. Double check, 2 potassium, 2 potassium, 2 nitrate, 2 nitrate, 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. Great, we're balanced. Now the next step is determining, did we actually have a reaction occur, or are we all just looking at ions running around in solution? And for that, we need our solubility rules. And so we look at our solubility rules and we say, okay, for magnesium nitrate, is it going to be soluble or insoluble? Well, it contains nitrates, which means it's always soluble. So this is going to be an aqueous product. And then we look at potassium sulfate, soluble or insoluble? It contains potassium, which is always soluble. It also contains sulfate without an exception, so it is still soluble. If we have a reaction where everything is aqueous, we just have a bunch of ions in solution, and we would say that is no reaction. All right. because nobody's forming anything new. We started with aqueous ions, we ended with aqueous ions. All right, now let's look at the next set. So again, on this one, the cations are going to switch places. And we're going to end up with silver chloride and sodium nitrate. We still want to confirm that we have charge neutral compounds. So we check our charges. Charge on silver is +1. It's always +1. It's one of the only transition metals that has a set charge. Charge on chlorine is -1. Yay, it's already charge neutral. Look at that. Sodium charge is, nitrate's charge is, oh, already charge neutral. Look at that. So we check our balancing. 1, 1, 1, 1, 1, 1, 1, 1. Oh, hey, look. We're also already balanced. This reaction's awesome. So now we decide, okay, did we have a reaction? Are we going to form a solid precipitate or not? And to do that, we look at our solubility rules. And we have silver chloride. Is it going to be soluble or insoluble? Well, it contains chlorine, so we find chlorine over here. And that would normally mean it would be soluble, but since it's bound with an exception, that means it's insoluble. So this is going to be a solid. We're still going to check the other product because we could potentially form two solids. So we go to this one and we look at sodium nitrate. Oh, well, it contains sodium and nitrate. Both of those are always soluble without exception. So this is aqueous. So this one is a precipitate reaction. PPT is shorthand for precipitate. When we have a precipitate reaction, we can write everything out the way that we're accustomed to. So all of the molecules reacting with each other and forming their products. That's called the molecular reaction. Or we can write out the ions that are interacting in solution, because what we're really looking at here for silver nitrate, when we put it into water and make that aqueous solution, we're no longer looking at molecules of silver nitrate. We're actually looking at silver ions and nitrate ions. Same thing for the sodium chloride. We're looking at sodium ions and chlorine ions. And so we can write out all of the ions that are interacting, and that's called the complete ionic equation. And notice in that complete ionic equation, who doesn't break apart into ions? Our solid. If it's insoluble, that means it doesn't dissolve. If it doesn't dissolve, it can't dissociate. And so anytime you have a solid precipitate, it just stays together as a molecule and it's solid. It's just going to sit there at the bottom of the reaction flask and be there. Everybody else is going to remain in ion form. Same thing is true if you have liquids or gases being formed. They are not going to break apart into their component ions. Now, what do you notice is kind of interesting about all of the ions up here? Do any of the ions appear on both sides of our reaction? We start with a sodium ion, we end with a sodium ion. We start with a nitrate ion, we end with a nitrate ion. Okay, well, if we start with it and we end with it, and it's in the exact same form, has it done anything? No, it just kicked back and watched what's happening. Ions that do that are ions at the beginning, ions at the end, they just kick back and watch what was going on, are called spectators. Just like your sports fans that kick back and watch from the stadium and tell the quarterback how he should be playing the game. That's what they're doing. They're just kicking back, watching. Those spectator ions, while they are still present in the solution, are not doing anything for the reaction. So they're not really of interest, oftentimes, for the chemist. And so once we identify our spectator ions, we can omit those to get what's called the net ionic equation, where we're only looking at the two reactant ions that combine to form something new. And we take out all of the spectators. Leaving behind a very simple equation. Excuse me. Okay. And so as you're looking at these reactions, they're going to be set up very similar. You're going to be given a set of reactants. You're going to be asked to predict their products, determine whether you've had a reaction occur, so did you form a solid or not. Based off of that, determine the complete ionic equation, so writing everybody out that was aqueous as their ionic forms, and then identifying the spectator ions and writing the net ionic equation. Would like for you to give that a try. So what is the precipitate that forms when you have lead nitrate reacting with potassium sulfate? So yes, I've already told you, you are going to have a solid, so be prepared for that. You don't even have to guess. And then I want you to write out the molecular equation, the complete ionic equation, or just the ionic equation it's sometimes called, and then the net ionic equation. And tell me who were the spectators. So who was an ion at the beginning, who was an ion at the end, and you took them out to get to the net ionic. So most of you have got to the part where you've identified your precipitate, and it is the lead compound. So lead, and remember, for this reaction to occur, you're going to have your cations switching places, right? And so potassium and lead are going to swap partners. So this is going to be lead with sulfate. And this is lead 2, because this is nitrate, which has a -1, but it took 2 of them, which means this has to be lead 2+. This is sulfate, so it has a 2-. They're already charged balanced. Potassium's going to come over here and hang out with nitrate. +1, -1. Oh, those are already charged balanced as well. Then we look at our solubility rules, and we find, oh, hey, we got sulfate, but it's bound with one of the exceptions, which means that's our solid. It is not soluble. Then we have potassium, which is always soluble, as well as nitrate. So that's going to be aqueous as well. We're getting there. Okay. So this is our molecular equation. And if we want to balance this, we look at, okay, we have 1 lead, 2 nitrate, 1 nitrate. We need 2 of those. 2 potassium, now we've got 2 potassium, 1 sulfate, double check everything. Looks good. So now we're balanced. To write the ionic equation, or the complete ionic equation, we just take everything that's aqueous and separate it out into its component ions. Now, if it has a subscript, that means there are 2 of them. And we would reflect that by having a 2 coefficient. Right. And so when lead nitrate breaks apart, and again this is lead 2 nitrate, we get a lead ion with a 2+ charge. That is aqueous. We get the nitrate ion, which has a -1 charge and is aqueous. But we don't get just one of those when it breaks apart, we get 2. And we would say that by having a 2 here. Okay. So what happens when potassium sulfate breaks apart? What do we get? Two what? So 2 potassium +1s, and those are aqueous. And what else? And a sulfate ion, so SO4 2-. So that's all of our reactants. All right, so we break them apart into their component ions if they're aqueous, which means on our product side, we have lead sulfate, solid. He does not break apart because he's solid. And what about our potassium nitrate? Well, he's aqueous, so he breaks apart into potassium and nitrate ions. But how many? 2, because we have 2 molecules of that being formed. So you're going to put that 2 in front of both of these. All right. We can now identify who's our spectators. So who was an ion at the beginning and still an ion at the end? These 2. Really easy way to figure that out. Look at the end. Who's still an ion? Those are your spectators. To write your net ionic equation, you just erase your spectators. So the net ionic is going to be lead 2 plus, spectator, spectator, sulfate 2 minus, forming lead sulfate. Okay, not so bad. All right. This is important enough. I'm going to give you another chance to try it. So we're reacting potassium sulfate with calcium chloride. So remember, your cations are going to swap partners. guys are on it. So you were able to quickly identify that you're going to form calcium sulfate. Sulfate is normally soluble unless it's paired with, oh look, calcium, which means it's going to form a solid. So if it's on the chart and it's an exception, that means it's going to form a solid. And so that is our precipitate, calcium sulfate. And we've got potassium chloride, which is going to be soluble because potassium is always soluble. All right. Our ionic equation, we're going to break all of these apart into their component ions. So we have 2 potassium plus 1s that are aqueous, and a sulfate 2 minus that's aqueous, calcium 2 plus aqueous, 2 chlorine minus 1s that are aqueous, forming calcium sulfate solid. Again, remember, do not break apart your solids, liquids, or gases. Those are going to stay together. And 2 potassium ions, 2 chlorine ions. Something to point out, a good way to check yourself on writing your ionic equation to make sure you have the correct number and your coefficient, it should still be balanced. If you've done it correctly, it should still come up to be balanced. You've got 2 potassium ions, 2 potassium ions, 1 sulfate, 1 sulfate, 1 calcium, 1 calcium, 2 chlorine, 2 chlorine. So it should still come out balanced. That's a good way to check to see if you've got your coefficients written correctly in your ionic equation. Our spectator ions are the ones that are still ions at the end here, so potassium and chlorine. So taking those out, we're left with calcium reacting with sulfate to form calcium sulfate, and our spectators are potassium and chlorine. Now your question may be, does it really matter if I write calcium ion then sulfate ion? No. I'm not worried about it. The chemicals aren't worried about it. In your homework program, though, they may specify that they want to have it in this order. So keep an eye out for that so you don't arbitrarily get them marking you wrong for something that you did correctly, but they have a preference on how they're going to grade. Okay.
How important is that ionic equation?
This one?
Because from the molecular equation, we can figure out what the solid is and who the spectators are from that.
Yes.
I mean, I guess probably for Alex, we need to probably know how to do an ionic equation.
The ionic equation is nice because being the intermediate step between these two, it helps us realize that we really do have all of these ions in solution. They are still there.
Right.
But as for getting through a question on Alex, if you're just asked the net ionic, just do the net ionic. If you can do that. Intermediate step, you may be asked for it though. All right, which brings us to the expression of how much solute do we have in our solvent, which is also known as the concentration. So how much is present in a given amount. There are lots of ways that we represent solution concentrations, but the overall idea is always this concept of how much solute do we have in a certain amount of solvent, or a total amount of solution. And depending on how we choose to express those units, we get different concentrations. So you can have what's called a mass percent concentration, which in that case you're going to have grams of solute over grams of solution. And the grams of solution is going to be the mass of your solute plus the mass of your solvent. Times 100%. This is also known as a weight percent. So you may also see this written instead of M, M, you may see this written as W. And in fact, this is a little more common in the chemistry literature than this even. So this is a weight percent. Okay. The useful thing here to recognize as well, you can calculate the mass percent given the mass of your solute and the mass of your solvent. If you're given the weight percent, you can also use that to determine how much of the solute is in a certain amount of solution, using the fact that if it's a percent, and we assume that the total amount is 100, the given percent value goes on top here. So if I have, for example, a solution that is 12 weight percent sodium chloride, what that really means is that there are 12 grams of sodium chloride per 100 grams of my solution. Okay. Very similar to this weight percent idea is volume. Since we'll often be using liquids, we can use the volume, so liters or milliliters, as long as they're matching, to get a volume percent. And in that case, it's the volume of the solute over the total volume of solution times 100%. And again, we can use the given volume of a solute and the given volume of solution to calculate the volume percent, or we can use the volume percent that's given to determine how much solute is present in a given volume of solution. And again, we assume that the total volume is 100% since we're dealing with a percent. So again, if I had a 15 volume percent hydrochloride solution, what that's saying is I have 15 milliliters of HCl per 100 milliliters of solution. These are conversion factors. And so if I was given a volume of solution, I would use this as my conversion factor to get how much volume of HCl I had in that amount of solution. So I would set up my bridge like that. Or we can use a combination of mass and volume, or weight and volume. So if I were measuring out sodium chloride, I would get a mass of sodium chloride, but if I'm putting it in water, I'm probably going to measure the volume of that water rather than the mass of it. And so you can do a mass volume percent or a weight volume percent. And what that means is you've got the mass of your solute in grams per milliliter of solution. And this is the only one where you absolutely have to specify that particular unit. Because of the other ones, as long as the unit's matched, you are fine. But because we're going across the two types of measurements, we're doing a mass and a volume, you have to match the explicit units of grams per milliliter. And so if you were given a mass volume percent, you could think of that as, well, if I had a 25 weight volume percent sodium chloride solution, what that's really saying is I have 25 grams of sodium chloride per 100 milliliters of my solution. Those are the three easy concentrations to get directly from your lab instruments. But remember, we don't have a nice way of relating mass or volume to our chemical equations. So as chemists, we more frequently use molarity. And molarity relates the moles of solute to the liters of solution. And so we're still going to weigh out how much we're putting in, but we're going to go ahead and use the molar mass to convert that to the molar amount that we're putting in the measured volume of solution. And since it is a fractional unit, it's going to be moles per liter, we have a means of using this as a conversion factor. And that's where we'll pick up next time.